Okay, so thank you very much. So maybe I should have printed the old in a larger font and the new in a smaller font, but...
It is capitalized.
Oh, that's true. Yeah, thanks, Erich. First of all, I should state that it has nothing to do with eigenvalues. Yeah, so I'm talking of spectra. It has nothing to do with eigenvalues. Okay. So this was the point when I would expect half of the audience to leave immediately. Okay, so. I've turned off. Okay, so what's the agenda for today? So first I want to introduce the asymptotic spectrum of tensors and its relation to matrix multiplication. In particular, I will spend the first few slides on really basic stuff on the exponent of matrix multiplication and fast matrix multiplication. So don't worry, Chris, I will not grab away too much from your talk. And I will really spend all stuff on the basic things because that's what's lying at the heart of everything. And once you start with this asymptotic spectrum, you forget about everything. But it's really important because it's underlying everything. And this is essentially based on a sequence of 3 papers by Volker Strassen, so around 1987 to 1991. And essentially, this concept of asymptotic spectrum is not that well known. Yeah? Of these papers, you know the laser method, maybe, so that's what's known, but the rest it's rather unknown. Maybe one reason for this is that I have the impression somebody told Strassen in 1986 that category theory is a cool thing. Yeah? So therefore it's not so accessible, but I will try to present it in a very basic way. Underlying everything are so-called stone preorders. I will define what this is. And so the second part of the talk, this is based on some unpublished work with Manuel Aurora, who's now a postdoc by Chris Human's group. And so we are currently, or at least I am currently, in the process of writing everything up. So not everything, it's not completely finished. And essentially there we try to find stronger preorders for which you can study asymptotic spectra. And stronger preorders, they have the property that you might get better algorithms. Yeah? You have more algorithmic tools at your hand. On the other hand, this is an unpublished idea that Strassen told me last year. So I will just very briefly sketch this because it's not my idea. You can also look at weaker preorders. Then the math gets easier. And it's much easier to determine these asymptotic spectra. Yeah? So these are the 2 possibilities that we have our hand now. And first I will introduce the asymptotic spectrum. Then I talk about our approach. And if there's still some time left, in the end I will just briefly talk about Strassen's idea. And if even more time is left, then you will have a longer break. So that's the problem that's lying under everything. Yeah? So it's matrix multiplication, you know all that. We have 2 matrices, we want to compute their product. It has the usual formula. The entries are variables, and our allowed operations are these basic arithmetic operations. And what will also play an important role later on, so there's Strassen's algorithm. Yeah? So this is this way of multiplying 2 by 2 matrices. You know these 7 products here, and you can write the entries of the result as linear combinations of these 7 products. Yeah? It's not obvious, but you can do the calculations. Yeah?
7 is out of order.
7 is out of order?
No. He's asking an obscure question.
I see, okay.
I'll tell you.
Sorry I couldn't come. I wanted to come. So, so Strassen, that's the whole story. So you trade 7 multiplications. So you have 18 additions, so you trade 1 multiplication for 14 additions. And so the question is, of course, what's this good for? And the observation is that Strassen's algorithm works over any ring, so you can do this block structure thing. You cut your 2n by 2n matrices into n by n blocks, and then you can just recurse. Yeah? And then you get this recursive inequality, and you get the result that you can multiply n by n matrices with order 2 to the n.81 multiplications. That's and that's now where tensor rank comes into play. So this is just very concrete. We here in the first part I will just work with coordinates and everything. Yeah. So some bases showed up, and I will just take them. So we have some bilinear forms in x variables and y variables. And we write down this trilinear form here. And then these structural constants there, they just form our tensor. And then we can reformulate the question whether some set of bilinear forms has a certain bilinear complexity as a tensor rank problem. Yeah? And we also have seen this before, so we have, this is our ambient space, we have these triads, they are the rank 1 tensors, and then the tensor rank is the smallest r such that they are rank 1 tensors t1 to tr, such that I can write my t as a sum of these tensors. And the two important properties of tensor rank is, so we can perform the direct sum of two tensors. So as a picture, it looks like this. And what you algorithmically should think about this is, so you have matrices A and B and matrices C and D, and you want to compute this independent multiplications. And then we know that the rank is sub-additive. And for the rank, it's an open problem whether it's additive. Yeah? So can it really help to multiply A times B when you also know that you multiply C times D in parallel? Huh? But for the concept of border rank, this really helps. Now there's an example by Strassen, which we will also see later on. So for border rank, it's really strictly sub-additive, and for rank, it's an open problem. That's Strassen's additivity conjecture. And the other thing is when you perform the tensor product of two tensors, it's also sub-multiplicative. Huh? So for just abstract for concrete tensors, tensor product somehow looks like this. But for matrix multiplication, we have the important property that if I take the tensor product here of two matrix multiplications, I get a matrix multiplication again. So that's very important. And just to make sure that everybody has seen a matrix multiplication tensor, so here's the tensor of 2 by 2 matrix multiplication, and it looks like this. Yeah, so the third dimension is color-coded. Yeah, so we have a blue layer, a red layer, a green layer, and a gray layer. And so this tensor is just, you have a 2 by 2 identity matrix in every layer, and you just shift it into all the 4 possible positions. And in general, it's given by this formula, the entries where delta is Kroneker's delta. And if you now look from the top of this tensor, or you look from the side on this tensor, you will see that you will always see a matrix tensor. Yeah? So the rank of a matrix tensor, it's invariant under permutations. Yeah? But also you just can compute the dimensions of the matrices. So these are the two important things about matrix multiplication. Yeah? Whenever the rank, you know the rank of, say, us, maybe I didn't tell you. So this thing is the tensor of k times n matrix multiplication with m times n matrix multiplication. Yeah? So this is the usual notation. And so just by looking at these pictures, and if I look at the different sides on this tensor, you'll see that so this, no matter which thing you will take, whether you want to multiply k by n matrices with m times n matrices, or you want to multiply n times k matrices with k times n matrices, the rank is the same. Yeah? We always get a matrix tensor. Nowadays it looks trivial, but there's an old paper by Hopcroft-Musinski where they do the explicit calculations over 20 pages or something like this. Yeah? So it really took some time until one saw this picture behind everything. Yeah? Yeah, and then essentially you have the observation if you take tensor product, that's just recursion. Yeah? So the algorithmic idea of this tensor product is recursion. Yeah? And then you can just take Strassen's algorithm, you form a huge tensor power of this, and then you get 2 to the s times by 2 to the s by 2 to the s matrix multiplication. That's everything. That's the algorithmic ideas behind everything. And then you know that this is bounded by 7 to the s, and then you could do the calculations, and you will see that you can do matrix multiplication in order 2 to the 2.81. And that's the usual definition of matrix multiplication exponent. So omega is just the infimum over all tau, such that the rank of the n by n matrix multiplication tensor is bounded by n to the tau. And by this thing here, and the subadditivity and submultiplicativity of rank, we get that this exponent is bounded by 2.81. Yeah? So that's the whole story behind everything. Okay. And so for now on, we just will concentrate on tensors. And it's very important. So these tensors, they live in some ambient space, U, tensor V, tensor W. And in the first 2 slides, I will just write them explicitly to every tensor, but you should always keep in mind that they live in some of these space, and they could, for the same tensor, they could live in different ambient spaces. And so we perform direct sum, we perform tensor product, and third important tensor beside the matrix multiplication tensor will just be this diagonal tensor. Yeah? So this is, you just take the space K to the R, and this is essentially the three-dimensional identity matrix. You just take this box, and you just have ones on the diagonal from one corner to the opposite corner. And what we want to do is now we want to compare the complexity of such tensors. And this is done by restrictions. So we have a tensor T, and we have a tensor T prime. One lives in the vector space U tensor V tensor W, and the other one lives in the vector space U prime tensor V prime tensor W prime. And then we call T a restriction of T prime if we can find homomorphisms from U prime to U, and V prime to V, and W prime to W, such that T is this thing. So to take the tensor product of these three homomorphisms and apply it to T prime. And essentially this just means that you can write T prime as a decomposition of triads. These are vectors, and you can, to every three components of this triad, you apply the homomorphism A, B, or C. In particular, if T is a restriction of T prime, the rank of T is less than T prime. And you call T and T prime isomorphic if you can choose A, B, and C to be isomorphisms. And then if they are isomorphic, they are algorithmically equivalent. Not even algorithmically, but also structurally. If two tensors are isomorphic, then essentially from a mathematical point of view, they have the same structure. But if you think you take a tensor T and you just embed it in some larger tensor and you just pad with zeros, algorithmically this should be the same tensor, right? Because you just have added some zeros and did nothing else. But of course, mathematically they are different objects because they live in different spaces. And so this is why we need this concept of equivalence. Yeah, so you call a tensor T a null tensor if it's just filled with zeros. Yeah? If you have some space where it lives in, and you have just a zero tensor in the space. And then we call two tensors T and T prime equivalent, denoted by this sign here, if we can find null tensors n and n prime, such that the direct sums are isomorphic. You can think of it as you have these tensors, we pad them, they might live in different spaces, but we pad them with zeros such that they have the same size. And then we have the spaces they live in have the same size. And then we have to find an isomorphism between these two tensors. That's what we want. And equivalent tensors, they are equivalent from an algorithmic point of view. They essentially have the same complexity, all in the same structure. And it's fairly easy to see that if S is a restriction of T, then the rank of S is bounded by the rank of T. And if S is equivalent to T, then the rank of both is the same, because then you have a restriction from S to T and a restriction from T to S. There's another way of defining equivalence, namely by looking at what is called a concise version of a tensor. So whenever you have a tensor T, then there's a unique space. Whenever you have a tensor T, which lives in U tensor V tensor W, then you can find a unique space UT tensor WT. So T is maybe not good. Let's call it C. Concise WC, such that T lives in this space, and this has a minimum dimension. So this is a subspace of this thing. Yeah? And when you choose UC, VC, and WC having the same dimension, then two tensors are equivalent if their concise versions are isomorphic. Yeah, that's an equivalent definition. And the important thing, what I want to do here now is, when you think about the tensor rank problem, you want to produce absolute statements about tensors. Yeah? You want to write something like the rank of this tensor is bounded by 123 or something like this. What we are doing here, we are just producing relative statements. Yeah? We want to have something like this. The rank of the one tensor is bounded by the rank of another tensor. So these are the statements that we want to produce. But it will turn out that we also get absolute statements out of it, because if you choose this tensor T here to be this diagonal, one can show that a tensor is a restriction of a diagonal if and only if the rank is of a diagonal of size R, if and only if the rank is bounded by R.
Can you recall the definition of smaller or equal between tensor?
What definition of?
Just previous, he wants to see the previous slide.
To see the previous slide again. Restriction.
It wasn't necessary.
That's a restriction.
A mouse, so if you can pick one.
Okay.
And what we do now is essentially we form some semi-ring. Yeah? So the elements in the semi-ring are our equivalence classes of all the tensors that are equivalent. And then the addition in this semi-ring, this is just, as you take the two equivalence classes, you take two representatives, you form the direct sum of these representatives, and you take the equivalence class again. And the same you can do for multiplication, and multiplication is essentially tensor product. And then, because you have all these laws about direct sum and tensor product, you see that this forms a semi-ring. And so the equivalence class of the null tensor, or of the diagonal of size 0, that's a null tensor. This is the neutral element for addition. And the diagonal of size 1, that's the neutral element for multiplication. These are just simple calculations. And then it is quite easy to see that in a standard way.
How is one defined if you have different size UVW?
What do you have defined?
This element 1.
Yes.
How is it defined when you have different
Just enlarge the spaces so
I guess just enlarge the spaces.
Okay.
So I just pad.
Just okay.
This is the notion of equivalence.
The diagonal element with all the bases.
yeah.
It's just the notion of equivalence, where we just look at equivalence classes, so we can always pad. And we can extend this to a commutative ring in some standard way. Yeah? So we have the same multiplication law. We know if S and T are the same, then S and T are equivalent. And for all A and B, you can find S and T such that you can write A as the difference of two equivalence classes. Yeah? That's essentially the same construction when you construct the integers out of the natural numbers. That's the same construction. What you need to work is the following observation. So if you have a decomposition T into such sum, so you can write T.
Any semi-group can be extended to a group.
Yes.
That's what you're doing.
This is, I think, sometimes called Grothendieck ring.
Yes.
Exactly.
Exactly.
Injected, and that's why you need to have this cancelling property. Otherwise, it's not injected.
Exactly.
So what I need here is that if it is this decomposition, so if I have one such composition, and there's another decomposition into. These things are indecomposable in the sense if I can write them as the sum of two different elements, one of them has to be a null tensor. Yeah? Then these two compositions are essentially the same in the following sense that R equals Q, and this is a permutation of that. Yeah? So this is what you need to make everything work. But this is just, you can just do the calculations.
This is for the B plus, not for B.
Sorry?
That's for B.
B plus.
I need it for B plus and I need it for B. So I need it for both. Okay.
No, but for B it will not be unique.
It's not clear that if you take the tensor product, the product that you have something like prime tensors that are with unique decomposition.
Not for.
It's just for the addition.
Just for the addition, yes. Just for the addition. I don't need it for multiplication. It's not clear.
Yeah.
Multiplication is not clear, but it just needed for addition.
Why do you need it?
This is a statement, and because this is true, this is a true statement, but I need it for the construction.
And do you need it? What is R?
You see the tensor for the construction.
No. R. This is what this thing here. Which R?
Yeah, what is it?
R is just you have a tensor T, and you can write it as this sum. You write it as a sum of indecomposable tensors. And indecomposable means that you cannot write these as a sum. Yeah? So these are.
Can you claim this is always unique?
And for tensors, this is unique. If these t's are indecomposable in the sense that you cannot write them as a sum, again as a sum, as a non-trivial sum.
I think there's some examples. Propositions.
That's unique, and because it's unique, this construction works.
Well, you always get the construction, but having certain properties you need.
Yeah, I can do the construction, but I would to have the properties that I want. I need this.
So what would happen if the uniqueness fails? Like if somebody produces for you a tensor with two non-equivalent decompositions?
Well, then the equivalence class of S could equal equivalence class of T when they're not equivalent tensors. You could collapse.
The construction works, but I need essentially want to have this because there are all these algorithmic properties underlying this. Because in the end, you also want to have algorithmic statements. And of course, this B has also universal properties. So when there's another ring, then you can break a bracket and this factors through some endomorphism, so all the usual stuff. Yeah?
So maybe, sorry.
Yeah, sure.
If R is greater than the generic rank for the tensor, you expect there to be infinitely many decompositions into some.
So that's he's not.
No, it's direct sum. It's direct sum. It's not. We are not adding tensor. We're just taking direct sum. That's.
Sorry, I
just block decomposition. No, nothing. No. Yeah, and so as I said before, what makes this ring interesting essentially? So if R is a restriction of the diagonal of size R, then the rank is bounded by R of T. Yeah? So this is essentially always the question that we have in mind here. Yeah. This is what we want to study, so we should always ask ourselves, is this useful what we're doing? Yeah? And because if S is a restriction of T and T is a restriction of S, and S and T are equivalent, and if the equivalence class of two tensors is the same, then they are equivalent, restriction and rank extend to B. Yeah? So from now on, we will just forget about the tensors, we'll just look at equivalence classes and just treat them as they were tensors. And then restriction, this is a partial order on this ring B+, which induces the natural order on the natural order on the natural numbers. Yeah? In particular, this ring has characteristic 0, yeah? Because essentially these diagonals here, they play the role of the natural numbers. And then it takes some work to verify this. So but these are just some calculations. If A is a restriction of B and A prime is a restriction of B prime, you can add these two inequalities and you can multiply these two inequalities. And so this is again, essentially this is a direct sum of tensors and this is tensor multiplication, but when I'm thinking about the ring elements, I will just write it like this. And the third important property that one is that this ring is Archimedean in the following sense. So if A
Exactly.
is
yeah. That's cool. R equals 1 would work.
no, so fun? No, this one here, this is wrong. This is wrong. I don't need it. This is a typo. I don't need that. So if you just have any tensor A and B is a non-zero tensor, then you can find the natural number R such that A is bounded by R times B.
Positive.
Fine? A should be positive, so A should be in B+. So H should be greater than 0. Yeah.
Yes. And then, so it's Archimedian.
And that's quite easy to see because if B is a non-zero tensor, you can always degenerate one multiplication out of it. And then because the rank of any tensor is bounded by some R, yeah, you just take this R. So that's what you do there. And we also can always do, so restriction is invariant under permutations of the free spaces there. And you can also view this as in a very abstract way, yeah, so with Archimedean orders and positive cones. So whenever you have some ring, a commutative ring B, you call some subset P a positive cone if it's closed under multiplication, if it's closed under addition, if 0 and 1 are in P, but -1 is not. And you then can call this pair, you call it a pre-ordered ring. And essentially, you induce a pre-order in a natural way. So A is less than B if and only if B minus A is contained in P. And again, in this case, the ring B has characteristic 0. particular, if I take p and intersect it with the integers, I get n. Because I just can take 1, I add it up, and then I never will get -1. Yeah? Because otherwise -1 would be in p, so I create all the natural numbers. And then we call p Archimedian. If for all a and b, there is an r and n such that r minus a is in p. Yeah? So r is an upper bound for a. In this case, I can always write b as p minus p. Yeah? Because this upper bound r is always contained in n, and then I can just write I can just write any element as a minus r, r minus a. Yeah, so that's how I write it. And what you can also show that in this case, the intersection of p and minus p is an ideal, and you can factor out, and then you would get an ordered ring.
But shouldn't you require that p somehow generates b? Otherwise, I can have a very small p, and then it will not satisfy this property.
I think he does.
Right? See, you want p to be generating b.
You want b to be generated by p minus p.
Exactly. Exactly.
Yeah.
Yes.
That's got to be in there.
What do you want to
Well, if you don't have any restriction on p,
Yeah.
for instance, say just the natural numbers inside of a ring would satisfy that,
Yeah.
and then you wouldn't get all that you need.
From Archimedean, you would.
You need.
You need Archimedean.
Oh, you need.
I need Archimedean. So this only holds if I have Archimedean. Here I get just a...
P minus p.
Archimedean implies this.
Oh, I see.
Archimedean implies this.
In general pre-order.
Here, here just get a pre-order. There does not hold. Yeah?
Correct.
Because you can have an order that's not applicated,
Right. Exactly.
Okay.
which is okay.
And so we essentially have now this restriction order, and they have just this abstract order given by these positive cones. And then it's an observation. Was it in your thesis? I don't know. No. I wanted to look it up, but I forgot. Yeah? Okay. So there's essentially no positive cone in B that induces our restriction order. Yeah, so you have to. Yeah? So this positive cone induces some order, but this is the order which is our restriction order, which we defined in the beginning. And you can show that there's no positive cone in B that induces the restriction order in B+. And here's a counterexample. So this is a 2 by 1 by 1 matrix multiplication. It has rank 2. And 1.
For those who are not very familiar with B plus is a cone, right? It's a positive cone.
B plus is a semi-ring. B plus is our semi-ring that we constructed in the beginning of all the tensors, of all the tensor classes.
Is it like a positive cone or it's not?
Positive cone is a way to generate order. This order cannot be generated.
So the positive cone, we are looking for a positive cone which lives inside B plus. Yeah. Or inside B. Yeah. We're looking for some positive cone which lives inside B, and B contains B plus, because this is this extension to a ring. Yeah, and so for instance, then because these two equations hold, you can multiply them, and then you get that 2 times this tensor plus 2 times that tensor is bounded by 4 plus this tensor here. Because by the property that if I take a 2 by 1 by 1 matrix multiplication, the 1 by 2 by 1 matrix multiplication, get a 2 by 2 by 1 matrix multiplication. And then one can show that these matrix multiplications are indecomposable. Then here on the left-hand side I have 4 indecomposable parts, and there should be a restriction of 5 indecomposable parts, and that cannot happen. So we cannot find some positive cone in B that induces this restriction order. And therefore, we relax this restriction order to asymptotic restriction.
Can we just take a second to tell us what you're going to... I mean, you're introducing all this formalism. You have not told us why.
Yeah, because in the end, I want to use some a representation theorem by Kedison, Stone, and Dubois, which essentially you need rings and you need some positive Archimedean cone in this ring.
And what are you going to prove with the use of this Strassen theorem?
So I want to get some representation, and on this I can study the exponent of matrix multiplication.
Are you going to prove lower bounds, upper bounds?
Just structural theorems. Structural theorems.
Structural theorems.
Insights.
Insights. So currently we are only producing insights, nothing else.
Okay. Just insights into a number. Insights into a number. Anyway.
Also insights in the algorithms, because all the equations that I will later get on, they all correspond to algorithms.
What do you mean by format?
Format is the dimension of the spaces.
So it's an 8-dimensional space tensor, 6-dimensional space tensor.
Right, that's the format. Yeah.
Okay.
So that's and yeah. So
Sorry.
yeah, sure.
So, why can I not go from a 5 to 4 with a dimension? What's the contradiction?
Well, incompatible block structure.
It is a block structure, and if I have 5.
I think the argument is that you have this restriction, but both sides have the same format. So because they are concise, they are isomorphic. Okay, that's so. But then you have this uniqueness
Of this decomposition, so they would have to have the same. Yeah.
So it cannot be.
They have to be isomorphic because the format is the same, but they have a different number of terms in this unique decomposition.
Why did I? Because the original 2 on 1 is not less than or equal to 2, but equal to 2.
No.
No?
No, it's not equal. It's not equal to 2 because I don't know if it.
The
No,
bracket
it doesn't
2 on 1
matter.
equals bracket 2.
No, that would mean that I could degenerate the diagonal of size 2 by 2 of this.
That 2 is the 2, 2, 2. 2.
No, that 2. This is just the diagonal of size 2.
Okay, the bracket, that 2 used to be called bracket 2.
Bracket 2. Yeah. So because we forget about it, because there's natural numbers that I find in my ring.
But 2, 2, 1, 1 is not bracket 2 tensor bracket 2, 1, 1.
Yeah, this is the matrix multiplication tensor. That's the matrix multiplication tensor.
No, 2 bracket 2, 1, 1 end bracket.
That's just 2 copies. No, that's 2 copies. That's just a scalar multiple.
Okay, fine.
2 copies. And therefore we relax this to asymptotic degeneration. Yeah? So we say S is an asymptotic restriction, not degeneration, is an asymptotic restriction. If I take a huge tensor power of S, I can restrict this from a huge tensor power of T, but not 1, but I have a sub-exponential number of copies. And that's the usual thing that you find whenever you do produce fast matrix multiplication algorithms. For instance, by transforming border rank into rank, you get this stuff. Yeah? Then you would take nth roots of square roots, and asymptotically this thing would go away. And then so that's what lies behind all the modern or all the more sophisticated fast matrix multiplication is asymptotic restriction. That's what we're. So it makes sense to introduce this thing here, yeah? Because there's an algorithmic concept underlying it. In particular, if you can prove that, say, some matrix multiplication is an asymptotic restriction of some diagonal, then the rank of this thing is bounded by, so you get an upper bound of the exponent, like you would if you just would bound the rank, in exactly the same way. Yeah? So for bounding the exponent, asymptotic restriction is as good as just an upper bound of the rank for something. Yeah? And then you can show that this thing has all these nice properties that I want to have, like before, like restriction. And I just as a side remark, it also implies degeneration. So that that's again wrong. So somehow this is a copy paste. So I just copy it and just replace the symbols automatically. Yeah, it's exactly the same error.
So what's this triangle less triangle left?
That's degeneration. So that's essentially the relative version of border rank. Or as I think Chris will explain it later on. You can, here you can just state that S is contained in the
endomorphism, and one is closure under GL,
right,
one is
correct.
action of endomorphism.
Right. Okay.
That's not important here. That's just a side remark. And now we can show that whenever I can write some A, so this is just some preliminary stuff. So if I can write A as 2 compositions, so A lives in my ring B, I can write it in 2 ways. Then I can show that A1 is a asymptotic restriction of A2 if and only if B1 is an asymptotic restriction of B2. And now I'm defining what is called the asymptotic cone. So I take all the a's in B such that I can write A as A-1 minus A2, such that A2 is a restriction of A1. Yeah? So essentially these are, somehow this is positive, something positive. Yeah? As A2 is less than A1 and I'm taking the differences. And this thing contains the whole ring of tensors that we B+. And one can show that this is an Archimedean positive cone. So you have to prove this. Once you have this, and of course this cone induces this asymptotic restriction on my tensor classes. Yeah?
So the first lemma is what is interesting because it shows that you can extend this asymptotic order to the whole ring.
Yes. That's important. So this did not work for restriction, but it works for asymptotic restriction. So that's an important lemma. Yeah?
That's important.
That's very important. It should be read. Yeah. Okay.
No, but it's not. It's equality there, not less than equal to.
No. This just means if I can write A in two ways, then as a difference, then one the left.
That's right.
Yeah.
That's right.
Now I have everything. Yeah. I need a last property, namely what is called a stone preorder. And this is just this. So this is the property which you need essentially in the proof because for what we will do on the next slide. So I call something a stone preorder. Sorry, if for every A in B, I take an A in B, and suppose that for all n, I can find a P in n such that if I take n copies of A, I add 1, and then I can multiply this by some P, and I land in my positive asymptotic cone. Then already A has to be in this cone. This is called a stone preorder. I will not tell you for what you will need it. It's essentially needed in the proof of the next theorem. And an Archimedean, pardon?
Stone preorder, but where was the preorder?
P of the positive.
P of the order.
This will always give us an order. Yeah? So cone and order is now the same.
May I add some intuition? I mean, assume we could just divide by integers. Then P times A plus NA greater than or equal 0 intuitively. Then you divide. Then it means 1 over n plus A greater than or equal to 0. This is some continuity requirement. So we want to infer that A is greater than or equal to 0. I think that's the intuition.
Just to make sure, we saw, if I understand correctly, 3 main partial orders here.
Yes.
And you're going to concentrate on this one.
I'm going to take asymptotic restriction, yes, which is induced by the asymptotic cone. And such thing which in addition fulfill the stone condition is called a stone preorder or a stone cone. And then so this is what we now worked. So now in this situation we have this ring B, this commutative ring B, and in this ring we have this stone cone. We can apply this structure theorem by Stone, Kedison, and Dubois. And here it's just formulated for tensors for our tensor ring, but it works for any ring which fulfills this property. Yeah? So if I have any semi-ring of tensors,
Subring or sub-semi-ring?
What?
Subring or sub-semi-ring?
A sub-semi-ring, yeah. Sub-semi-ring. It's a sub-semi-ring, yeah, sorry. Then I access some compact space and a homomorphism phi from our semi-ring into this, these are now the continuous functions, positive continuous functions on this compact space here, such that phi of s separates the points of the space, which means whenever I have two different points, I will find a function which has different values on these points. And for all A and B and S, A is a restriction or asymptotic restriction of B, if and only if phi of A is upper bounded by phi of B on the whole compact space. And just remember, so this thing here is just something which says something about tensor rank or just asymptotic restrictions. Yeah? And so if you now think a little bit, this is an amazing theorem. Right? The first glance is an amazing theorem, right? Because forget about tensors, forget about algebra, forget about everything. All you have to do is you have to just study functions, continuous functions on a compact space. Yeah? That's calculus.
the spaces.
Right. So that's
You sort of do it. I mean,
yeah. Well, no, yeah.
What is, but it's not. So
That's the problem. That's the problem. Yeah, that's exactly the problem.
This is like a real version
Yeah, yes, you.
of the Delphi-Nymark theorem.
Exactly.
That's exactly.
Exactly, that's what I was thinking.
Yeah.
So what is really
Yes, but Stone had earlier
for this,
representation.
I mean, you state it in its full generality, so this realization in the
Yeah.
form of
Yes, right.
functions on a compact space. What is really necessary?
What is really necessary? You just need a commutative. Even works for non-commutative rings. You just have to need a ring, and you need a stone cone in it. That's what we need.
So what about the fact that delta is very complicated and mysterious? Do we know anything about this?
Yes, well, this is exactly the problem. So delta, for matrix multiplication, I can tell you something about delta. But the point is, though, you know delta if and only if you know the exponent of matrix multiplication. So this will be the story, yeah.
So in particular,
Delta is some like real spectrum of that ring, but you have to know something about its structure to say what those
But I think there is more information. Omega is just for the multiplication of square matrices. If you look at multiplication of rectangle matrices asymptotically, there is some shape of delta which is also unknown, but there's more information needed, just one number.
Yeah. So you can of course, we essentially will now look at finitely generated rings, subrings of S. So you just take one.
Can you? And then phi becomes automatically injective, right? See, because if there is a kernel that will kill this relation.
Yeah.
But you say unique up to canonical homeomorphism, but I can artificially enlarge by delta by multiplying delta across, let's say, R.
R is not
No,
compact.
but S1 doesn't matter.
S1.
I can artificially multiply delta by S1, and I can.
I mean, delta is the real spectrum of this ring. It's sort of canonically defined by the ring.
Yeah, but the way it's stated.
Well, he didn't tell us what canonical homeomorphism he means by that.
What are the properties it has?
Right,
So
exactly.
until he says what that remark means, we don't know.
So
But he doesn't mean that.
yeah. So
No, exactly. No, I understand that. No, I definitely understand that. That's
yeah. So it's not everything. Yeah.
Need to have the separation of points.
We maybe should
No,
let
but
him
I'm saying that extend
we
it.
should maybe let him give his talk.
No, that's okay. Yeah, so I skipped some of the details, which I want to come to some certain point. Yeah, but it's a long way. Yeah, so it is the whole sequence of papers had 100 and something pages. So I have to skip some. I have to be imprecise in some cases. Yeah. And so what do we now do? Essentially, what do we now want to do? So we don't look at the whole ring of tensors, but we just take some tensors. So you could just take the tensor of 2 by 2 matrix multiplication. Yeah? If you take this ring, what does this ring generate? So you just take polynomials with natural coefficients. You can plug in the tensors. For instance, you get all the tensors of format. Get all the tensors of this format here. Yeah? So you could just look at this ring here. So it's simply generated by just this one tensor, and it already tells you everything about the asymptotic complexity of matrix multiplication, if you can understand this one. Yeah? So this will be the ring that we will look at. And so essentially we can now make our life a little bit more simpler. Yeah? So we essentially we take now a continuous map from our space to R to the Q. Here it would be just R, but we just map some element Z to phi of A1, which is a function, and we just plug in Z. Yeah? So therefore we essentially can embed the asymptotic spectra in some R to the Q, where Q, if I have a finite number of generators, is a finite number. In particular, here it would just be 1. This is an injective map. Since this is compact, this map is a homeomorphism of its image. So we take this image, I can take the inverse homomorphism, and then, well, if I take the composition here, this is an asymptotic spectrum of S. Yeah? And in particular, phi prime of A is J, which is the J's generator of my ring. This is just the J's coordinate function. And so this thing I call the embedded asymptotic spectrum of this thing here. It's contained in R to the Q. As I said, if I restrict phi of aj is the coordinate function restricted to my space. If I have P is an asymptotic restriction of Q, if and only if P is bounded by Q on my space for any integer polynomials P and Q. And the same is also true for restriction, but the converse here does not hold. And I can also describe my space here in some abstract way, because it's just the set of all equations that hold when P of this thing is a restriction of Q of this thing. Yeah? So these are tensors here. Because I know if aj is non-zero, that 1 is a lower bound for aj, and the rank is an upper bound, I also know that this thing here is contained in this space. Yeah? So it's contained in some Q. Also an interval. But I also know if I just take the formats here of my aj, then the corresponding vectors are also contained in the spectrum, which are called gauge points. So here's an example. Yeah? So what do I know? I just take my ring here. So I only have one coordinate here. And I take a logarithmic so there's a j standing here, but here I only have one. So I take a logarithmic embedding of my coordinates. So I will write my coordinates not as xj, but as 2 to the tau j. So just scale them logarithmically. And then I know that phi of 2 to 2, this is just 2 to the tau. Because I have only one coordinate in this ring, I will get this thing. Yeah? And I can just draw this polynomial here. It starts by 3, or this function here, it starts by 3, it ends here somewhere. And here it's, well, it has a unique 0, and that's just 2.81 something.
Sorry, what is this curve?
What I'm doing, I just want to find something out about the asymptotic spectrum by looking at Strassen's algorithm. And what does I know? This polynomial, or this continuous function here?
Yeah, it's 7 minus 2 to the x.
That's the function, 7 minus 2 to the x, or 2 to the tau, what I'm looking at. Yeah.
Oh, so that's phi.
So what have I learned by looking at this picture?
What have I learned by looking at this picture? You learn that the asymptotic spectrum cannot have points on this range here, because the function is negative there. But I know the function has to be positive on the asymptotic spectrum.
So translate it into what have I learned new about matrix multiplication that I did not know before I saw this picture?
So far you didn't learn anything new.
Okay.
At least not about matrix multiplication. Not about matrix multiplication.
Well, what have I learned about anything outside of the formula? All right, sorry. I'm criticizing you guys. I'm doing the same thing. Okay, continue.
You get extra minutes.
I don't. I can also just go on in the evening if somebody is interested. Yeah. Virtual tensors. So the point is, if I now want to also talk about 3x3 matrix multiplication, so I want to talk about these tensors, I would have to add them as generators there. And maybe skip this thing here. You can also take Schönhage's example, you get another equation. Yeah. So the point of everything is, you can also interpret all the equations, the algorithms that you have in equations on the spectrum. And then it's non-trivial to prove so that the asymptotic spectrum of matrix multiplication, that's really the interval between. So it's between 4 and 2 to the omega. Or if you want to look at it logarithmically, between 2 and omega. Yeah. But of course, as I said, the pessimistic view of this is, of course, I didn't learn anything new about matrix multiplication. So to determine this thing here, I need to know omega. What's it all about? But you can also look at it optimistically, yeah? Because now stronger mathematical tools might be available. Yeah? For instance, say you can prove I have such a ring. It's generated by one tensor, so it's simply generated. It has a certain property, maybe the tensor is tight or whatever. And then I can prove that the asymptotic spectrum is always a point. It looks like a perfect, reasonable, abstract thing. It has nothing to do with matrix multiplication. But then I would get that the exponent is 2 from such a statement. This gives you a machinery to think about this problem without having matrix multiplication in mind. That's maybe the strongest thing, because in matrix multiplication, I have the feeling we are stuck. We don't know any new of these equations here. Yeah. So, well, we have some new ones, but they don't hit the line here, but they hit it a little bit more there. Yeah, but nothing else has happened during the last 20 years. So this is what, in my opinion, makes this asymptotic spectrum interesting. It gives you an abstract way to think about matrix multiplication without having it in mind. You can also interpret the group theoretic approach, have funny functions. Just one thing. So far this was Strassen's work. Yeah, maybe. So what Manuel and I here propose is another kind of restriction which is stronger, because you get more algorithms out of it. So I call S to be an asymptotic disjoint copy restriction of T if, so the right-hand side is the same, I have a sub-exponential number of copies of T to the n, but on the left-hand side I don't have now S to the n, but I just get a bunch of copies of S out of a smaller power. The only restriction that I have is I have epsilon to the n many copies of powers of order 1 minus epsilon to the n. For any fixed epsilon, which just has to be bounded away from 1, so that's the important thing. And this here is just the size of this tensor here to make the dimensions that everything match. And obviously that this implies, this new restriction implies the old restriction, and for diagonals they are the same, so I get a natural number, so I can do the whole theory of stone preorders, and I get the same spectral theorem for this. And the question is, of course, why is this useful? Yeah? So this one should be. No, I get a different spectrum. No, in the end, they will be the same because they will just contain 1 point. But I don't know how to prove this. In the end, they will just contain the point 2. Yeah? That's the
religious belief that many people have.
That's maybe the religious belief, yeah, but I don't know. So why is this useful? Essentially, if, say, you can define now this new exponent, which is a relative notion, but you can define it. And what essentially get is you get an inequality like this. Yeah? So the old exponent is bounded by this new exponent of matrix multiplication minus 2 epsilon over 1 minus epsilon if I have this restriction here. And if you believe that this exponent, if you can prove that this exponent is 2, you also get that the old exponent is 2. If you get something larger, then you lose something. Yeah? And so the conclusion, so also this restriction is stronger, so you can have more algorithmic tools at your hand. You can still say something useful about the exponent if it's 2. So where comes this from? Yeah? So this is inspired by this concept that Cohen and Humans in the Soda 2012. Yeah, roughly, it's this concept of support rank what they have there. Yeah, and so they say that a tensor, the support rank of a tensor is bounded by R if the two tensors have the same ranks. You will talk about this? Yeah. Okay. Yeah, and essentially what you can show if the support rank of something is bounded by R, then this tensor A is this D restriction of the diagonal of size R. So that's essentially the important concept lying behind this modulo some technical side condition that you have here, which I will not define because I'm already out of time. Okay, so that's it from my side. I somewhat over time, but so I guess we had already some of the discussion during my talk, so we maybe can just should stop here. Thank you.
Okay, thank you. We have many questions and comments.
So is delta something like a toric variety? Can you take it to be like a toric variety?
No, what should?
It's just a complex set.
It's just.
Yeah, but I'm asking if it's not algebraic. Can you take it? No.
I don't know anything. We have to find out everything about delta. Yeah? You know it exists, but then you have to do the work for each of the ring that you're interested in.
What one should say, Strassen determined is there in some examples.
There are examples where.
Matrix multiplication.
So for some tensors, if you look at this algebra, you take univariate polynomials, modulo some polynomial, and so for this complexity-wise, we know everything about this for rank and border rank, and also we can determine the asymptotic spectrum of this thing. He also has some results about some preliminary results about the asymptotic spectrum of rectangular matrices. There we even don't know convexity, for instance. And even showing that this here, in this case, it's an interval, that's not trivial. Yeah? You really have to work for this.
More questions, comments? You're okay?
Well, I don't. Well, I'll ask it now, and you can decide whether it needs to be taken offline. So, can you give me a sequence of lemmas, any lemma you want, say 3 lemmas, that if you could prove those, then you could tell me something new about matrix multiplication using this format, formalism.
Just any lemmas, or are you?
Yeah, I mean, anything
for instance, you could.
it's reasonable that you might prove in your lifetime, because I don't see how this is going to give insight into matrix multiplication. It's kind of, seems to me you have a very concrete object and you're replacing it by a more abstract object that you can't even identify. So,
With respect to differential geometry, that's an interesting statement.
So you should think.
But it's
I'm
important
missing
to generalize. Sometimes
I'm perfectly happy, but I'm missing the punchline is what I'm saying.
So say you can.
Ignorance.
My interpretation of this is that the theorem tells you that there exists a complete set of monotones for any pair of tensors you want to compare. And now you can find it, and then this kind of gives you a way of describing it.
Yeah, Markus did not describe it, but there are things here that are useful. For instance, confirmation theory.
Surprising that this is.
Okay, I suggest we take this offline.
So far.
There's an analog and operator here.
Welche Definition?
So are you expecting this to lead to concrete bounds, or what's your hope from this? That's what I don't get. I mean, you proved concrete bounds, right? Yes. Concrete lower bounds.